So hi, we're going to talk about higher degree polynomials, and the first one we've got here is in general form, which really doesn't help me much. I could put it into my calculator and it would give me a curve, but the only thing I can really tell from this right here is that it's definitely going to have a y-intercept of -7. I can't tell much more from this. I will mention this is a third degree polynomial. We know this because that's the highest order on any of the monomials that's here. And as a reminder, a monomial is a term with a real number for the coefficient, some variable, and a non-negative integer for the exponent. And that can include multiple ones. What's not there, if I had like 2a squared b c to the third, that also is a monomial. But when we string a bunch of monomials together with pluses or minuses, we get a polynomial. So we can graph these, and it will make some kind of curvy line. It won't make it exactly like that, but it's not going to be this, which is what we're used to seeing when we're just doing a quadratic. What's more useful when we get for these higher degree polynomials is vertex form. So if I can write something y equals x minus 2, I'm making one up. This is not related to the one above. X plus 3, x plus 5. There's a lot of information that I can get from there immediately, and there's some I can get from there very easily. So first of all, I know where my zeros are. This has got 3 zeros. So if I was going to sketch out the graph here, I know that we'd have a 0 at positive 2, because 2 minus 2 is 0. So 0 times whatever this is will make y 0, and that's why we call it a 0, as we know at 2 it's going to cross that point. At -3 plus 3 will make 0, so at -3 it'll cross again, and at -5 it will cross again. So there's going to be some kind of curve there crossing in each one of those places. The other thing I can find fairly easily without too much work is the y-intercept. The y-intercept is where, you know, y is equal to x is equal to 0 when we hit the y-axis. So if I just plug in 0 for all those, I'm like, oh, y equals 0 minus 2 times 0 plus 3 times 0 plus 5, which I'm sure you can see the short way to do that would just be, oh, I'm just multiplying those three numbers together. -2 plus 3 times 5. The y is going to cross at, it's a fairly large number, so oftentimes these scales will not be the same. On your calculator, sometimes you'll need to change the y scale in the window. So for those people using a calculator, you may have to go change the window, especially the y scale, to get everything to fit. So that's going to be a -30. So it's actually way down off the graph here if I do it to scale, or if I do it by tens, it might be there. 10, 20, 30 would cross it down at -30. Okay, so this thing's going to end up looking something like this. I don't know exactly. I don't know where this point's going to be. I don't know if this is actually going to be a local minimum, is what we'll eventually call it. But I can eventually figure those out, but I can certainly use my calculator to get closer. But the important is I've got a general idea of what this curve is going to look like simply by having this written in vertex form. So that's super useful. I can work in the other direction too. So if I get an equation that looks like this, I can actually figure out what this equation is without too much trouble. I've got a 0 here at 3, or -3. I got a 0 here at 2. I got a 0 here at 5. So we know for sure this is going to be y equals x plus 3, because the -3 has to make this thing equal to 0, and x minus 2, because 2 minus 2 is 0. We need the whole thing to be 0. Or finally, x minus 5. Now that's not exactly right. We don't know how much this thing has been stretched up or down. So there is some a factor out there that we don't know. Maybe it's 1, but maybe it's something else. Maybe it's -1. But we can figure it out because we have a point that we can plug in. In this case, we don't always get to 0, but in this case I'm fairly confident it crosses at 6, 0. So I can just plug that in. I can plug in the 6 for the y and zeros for the x. So very quickly that 6 equals 0 plus 3 is 3. 0 minus 2 is negative 2. 0 minus 5 is negative 5. So 6 is equal to a times, oh, it comes out negative 30 again. Is that right? Yep. And then when I divide this out, so that's a multiply, so when I divide both sides by negative 30, I think this is right, or did I, oh, not negative, it's positive. Positive. And so that's going to be 0.2 is my a. So my actual equation for this whole thing is y equals 0.2 times x plus 3 times x minus 2 times x minus 5. Okay, so that is the vertex form. Now I can expand that out into general form if I want to, but I can also leave it like that in most cases. Let's do another example. So I got this right here. Once again, kind of the same trick. Negative 7, negative 1, and 6 are my zeros. So I know this is going to be roughly y equals x plus 7, x plus 1, x minus 6. But I've got some a out there that I'm not sure about. So I'm going to plug in a point that I know. It looks like it crosses at 0. It doesn't actually quite cross through there, but it looks pretty close, so we're going to use that number. So I'm going to plug in 4 for my y. I don't know what a is. When I plug in 0 for all these x's, I get 7 and 1 and negative 6. And when I divide this negative 42 into this positive 4, I get approximately, not exactly, about negative 0.1. So this original equation is very close to negative 0.1, x plus 7, x plus 1, x minus 6. Okay, I'm going to do a quick aside is, what if I want to expand that? I've got to find a clean sheet of paper to do this on. Here we go. Okay, I want to expand that, put that in general form. I can actually use the area model to do that really quickly, so let me just remind you how to do that. I'm going to work from the backwards forwards. So if I do the x minus 6 times the x plus 1, I'm going to get x squared, I'm going to get minus 6x, I'm going to get 1x, I'm going to get minus 6. So that first one is x squared minus 5x when I combine my like terms, minus 6, I forgot my x. Now I'm going to do the box method again, except I'm going to do a 3 by 2, if you can see it here. And so what's left here is the x plus 7 that I haven't done. So I'm going to do the x plus 7, and so that's going to be x to the third minus 5x squared minus 6x. In the bottom part, it's 7x squared, it's negative 35x, and it's plus 42. And my like terms are here, and my like terms are here. So I have x to the third plus 2x squared minus 41x plus 42, if I've done all my math right. And then finally, I still haven't multiplied everything by the negative 0.01. So all this times negative 0.1, and so that's going to be negative 0.1 x to the third minus 0.2 x squared plus 4.1 x minus 4.2. That's if I've done all my math right. But I wanted to show you that this method will work with a 3 by 2. It actually works really great. Okay, last thing. I wanted to show you what happens when you've got what's called double roots. So if I just had this, which is really just y equals x, that's going to go through exactly through the, exactly through here. It's going to go straight through. Okay. If I've got x minus x, this is really the x squared function. And we know when we do that, it actually comes down here and it turns around. So I technically have a double root here. I've got a root of 0, 0, and I've got a root of 0, 0. So notice that bounces. Okay, so this one goes straight through, or it goes through. I don't know if it's straight, but this one bounces. This third one, if I was to graph this is really x to the third power. If I was to graph this in my calculator, it looks something like this. It does this weird wiggle here. And this really has what's called a triple root. It's got a root at 0, 0, another root at 0, 0, another root at 0, 0. So if you've got multiple roots, And if you've done some of these problems, you realize that sometimes I've got like two, if I have x minus 1 squared, that has a root of 1, 0 twice, because that's x minus 1 times x minus 1. So I've got what's kind of double root. So I'm going to have a bounce at 1, 0. Okay. So with that in mind, can we figure out what this thing right here looks like? Okay, this is kind of jumping way advanced. Okay, this is a bounce. So that's a double root. That's going to be x minus 2 times x minus 2. Okay, this is a little hard to tell, but it is a wiggle at 0. So this is basically x minus 0, or just x. This is x times x times x, because I'm hitting 0 twice. And if you want to think about it as x minus 0 3 times, it can. But that's x times x times x, which causes that wiggle at 0, 0. And then finally, low battery. So x times x, and this down here, this just goes straight through. This is x plus 3. So if I combine all these, I've got x to the third, x times x times x, that's what causes the wiggle at 0, 0. I've got x minus 2 squared, that's what causes the bounce at 2. And I've got x plus 3. That's the whole thing. I've still got a out here that I need to multiply by. But in the same way, if I have a point, like I do down here, I can plug that point in and figure out a. So I'm not going to solve for a, but I'm just going to show you how to set it up. So if I plugged in the negative 12.8 for this, a, if I plugged in negative 2 for that, and negative 2 for that, and negative 2 for that, and then I squared that, a times 8 times negative 4 squared is going to be 16, and then that's going to be a positive 1. All that's equal to negative 12.8. Eventually you can divide both sides and figure out what the a is. I'm going to leave that for you. Okay, ciao.